as the question says, a uniform rod pivoted at its upper end hangs vertically. It is displaced through an angle 60 degrees and then released. Find the magnitude of the force acting on a particle dm at the tip of the rod when the rod makes an angle 37 degrees with the vertical. Now, this is actually that vertical rod which has been displaced by 60 degrees and left, and we need to calculate the force at 37 degrees on the outermost particle, that is this one. So if we look at this particle with respect to this system, that is the rod, then there will be a centrifugal force outwards, and we all know that the total force equals to under root of tangential force square plus centripetal or centrifugal square. And we all know that the centripetal force, the tangential force Ft is given by mass, which is dm for this particle, into alpha L. So if anyhow we manage to calculate alpha, then we will be able to calculate the tangential force and put it over there. Similarly, we know that the centrifugal force or the centripetal force, in this case it's centrifugal because we are taking with respect to the rod, is equals to m, which is dm over here, omega square L. L because it is the outermost particle. So if anyhow we manage to find omega and put it in omega square and that again into fc square, then we will be able to calculate f. Now the problem reduces to calculate alpha and omega only. Now friends, if we look at this rod, now forget the particle, there is a rod which is actually rotating about this point or the hinge, and we need to we know that there will be an mg force at the center of mass in the downward direction, and so we can write a relation of torque over here, which will be I into alpha, that is torque equals to mg into, this is L by 2 distance because center of mass is L by 2, and this perpendicular distance, that is this one, is L by 2 sine theta, where theta is 37 degrees. Putting the value of I, it is ml square by 3 because it is rotating about the hinge or the end, into alpha equal to mg L by 2 sine theta, giving us alpha equal to 0.9 g by L. So this is the tangential acceleration that we have got over here, right? Alpha is the same because alpha is this for the rod, and these are the rotational parameters, so it will be same for all the particles. That's why we can say that for the outermost as well as the innermost, alpha is going to be the same. This is the condition in rotational dynamics. So for dm also alpha will be the same. That's why we form the equation for the rod only. Now also friends, we can take the situation between the point A and B, that is 1 and 2, when it was at 60 degrees and 37 degrees respectively, and we can do the energy conservation between the 2 points. And now we can write down the final energy, that is the due to the kinetic energy, half I omega square minus 0 equal to change in the potential energy, which is mg. This is now L by 2. It is L by 2 cos 37 degrees minus cos 60 degrees, giving us the omega square to be 9g by 10L or 0.9 g by L. Now friends, why we didn't take half mv square over here is because half mv square, if you are going to take, then you cannot take the half mv square of the whole rod with respect to the center of mass only. You must have, will have to integrate that for the each particle from 0 to L, and you will see that it will come different if you apply half mv square from center of mass. So this is a very important point. You cannot, in rotational dynamics, you cannot apply half mv square for directly center of mass to get the half mv square of the whole rod. That is why we had to apply the concept of rotational motion, and that's why we took the kinetic energy with that half I omega square, because omega is same for every particle. But in half mv square, v is different for each particle. So you cannot take the average to be the velocity of center of mass, right? That's why we took the rotational one here, because rotational parameters are same for every particle. So even if you integrate, that makes no difference. So putting the value of omega square from here into these equations and the value of alpha L into the F tangential, we get the force to be 0.9 under root 2 dmg.